we'll do a question with rings. But we'll start with some radicals. Okay. So let's say we have, let's just start simple. This is vinyl chloride. And so radical reactions are different from ionic reactions. So far, all we've done is ionic reactions. And in ionic reactions, we're always worrying about lone pairs moving, or double bonds becoming a lone pair and moving. It's all about two electrons moving as two electrons. Radical reactions are single electrons interacting. That's it. Now, why that complicates things is because the way we've been thinking about chemistry to this point, hopefully, is in terms of where's the positive charge, where's the negative charge. Now we don't have charges. We're going to have no charge generation at all. Everything is going to be neutral. That makes it a lot harder because it's a lot easier when you think, okay, I know where the charge is going to be and how it's going to react. When everything is neutral, it gets trickier. So the first rule of radical reactions is they follow the same rules as carbocations. Induction is not normally a big deal, but hyperconjugation helps, resonance helps, hyperconjugation helps, and bigger atoms stabilize them better. Came back to hyperconjugation again there. And resonance, of course, is always really important. But we'll just start with this one. We're going to just shine light on it. That's the symbol for light. It's H, and it's not H, it's the Greek letter thingy and then a lambda, but I can never get my Greek letters straight. It's a Planck, because it's basically Planck's constant times frequency of radiation that gives you light. And I don't know why we use that as abbreviation. It's some physics thing. Don't care. Okay, so we're shining light on this. And we're going to make a product. The product in this case is going to be a polymer, and we're going to discuss how we got there. And we can abbreviate that like that. Just see there's a lot of repeats of this thing. Repeat stuff in brackets. N times. What is n equal to? Who the fuck knows? It equals something. It's more than one, and it's the number of repeats. Depending on the precise conditions and everything that's set up there, you can get various values. Normally we use that if the number is over about 5 because it gets really irritating to write things 5 times. It could be irritating to write things 3 times. I gave up after 3, so maybe after 3 is fine. Whatever. There is not going to be so there's not going to be a radical. This is the product. There's no radical in the bracket. This is the product. The product has no radicals. I don't need to worry exactly about how the N groups are dealt with. Notice I'm being very iffy about what's going on in the end here. I should probably write H and H. But there's no radical at this point. When we're drawing the mechanism, we normally don't have the brackets because we normally only draw the first couple of additions. Okay, so every radical reaction is broken up into 4, I'm going to say 4 steps at the risk of being slightly confusing because the first 2 might be the same. So I'm just going to write down the 4 steps: activation, initiation, propagation. Now I think some of you guys saw this in high school. Some of you didn't. Termination. And I'm going to write working definitions of each of these steps. The H's are not carbons. Carbons. Why are the H's not carbons? There's just something stuck on the end. Like there's H's here and here. And so I'm sort of representing these H's. Because there's got to be an end to it, and a C can't be at the end because a carbon needs to be attached to something. Hopefully we'll make this sense of this, Amanda, if we go through this. So make two radicals out of 0. Initiation is very similar. Make a radical involved in propagation. Out of things not involved in propagation. I want to be broad with this because it covers two of them. Species. Okay. It's A. So this, I think, is often where it gets confused. That's why I split it into two. They can be the same step. In our example here, they are going to be the same step. We are going to activate and initiate together. But they can be different. And we'll see some examples where they're different. And it can get confusing when we say, hey, this is initiation. You go, that doesn't look the same as this. There seems to be other stuff here. It's because there can be other stuff there. So sometimes we need to make an initiate. We need to use what confusingly is called an initiator to initiate the reaction. And the activation step turns the initiator into radicals. Then the initiator turns species that are involved into propagation into radicals, and those can do propagations. And when the initiator turns things, I'm smiling because it's really nasty and the language is tough. When the initiator turns things that are involved in propagation into radicals, that's initiation. But turning on the initiator in the first place can sometimes not be initiation, and that can get confusing. So I am splitting it up, although those first two steps can be combined into one step often. It is in this example I've got here. Propagation, this is where you get your product. One radical becomes one radical. No more than two steps. You can never have more than two different reactions in your propagation. We'll discuss precisely why, but it comes down to radicals react with the most reactive thing. And once you've realized that, go like, yeah, nothing else is possible. You can only ever have two, and we'll see a moment of that later. And terminate, and this is where you get your product. Your product comes from propagation. So this is another thing that's confusing, because the last thing you write is termination. In every reaction up to this point, the last thing we wrote was the product, because you walk all the way through the mechanism, you stop when you make the product, it's nice and stable, it's even, you're done. Here, the termination is the last thing you write, but it is not your product. Termination is a minor thing that happens. Your product is formed during propagation, not during termination. Two radicals become zero. So activation, to make two radicals out of zero radicals. Propagation, make one radical out of one radical. Termination, make zero radicals out of two radicals. So we turn the radicals on, the radicals propagate, we turn the radicals off. Simple, really. Okay, let's walk through this example. Okay. So fundamentally, what we are doing in a radical reaction if we think about it, we've got a pi orbital, which is our lowest energy, which is our highest energy orbital. It's got 2 electrons in it. And then we have a pi star orbital, which has got 0 electrons in it. So far, when we've been trying to break a double bond with a nucleophile, like with the carbonyl chemistry, the way that worked is because the nucleophile came in, donated 2 electrons to our pi star orbital. It broke the double bond. That's not what's happening here. What's happening here is we're going to put energy into the system, in this case light. And we elevate an electron into the pi star orbital. We promote an electron, we put enough energy into the system that an electron jumps up. Now suddenly, we've got 2 orbitals here. We've broken the double bond, and we have 2 orbitals with 1 electron in each of them. And that's what happens. So we call this homolysis. Breaking the same. And what we do is we promote an electron, we break the double bond, 1 electron goes to the left, 1 electron goes to the right. They're each sitting there in an orbital alone. There's the orbitals alone. Now, the most likely thing that will happen is that pi star orbital electron will go, this is not fun. I don't want to be at a high energy. I am going straight back to the product, the starting material. Whee, straight back. That is by far the most common thing that happens when you get this kind of promotion, kind of chemistry with light. But occasionally, this electron sees another molecule, and instead of falling down, it reacts. The end groups are always weird, and we're going to have a weird end group here, and that's going to resolve itself. That's why I'm always sketchy about what's going on with the end group. Okay, so it reacts. This was a bad example. I should not have started with a light accelerated example. I'm going to finish it. We're not going to use light to promote electrons for a lot of this stuff, and so I probably shouldn't. This was a mistake. I'm not going to finish it. This is a stupid example. We're not going to use light promotion anyways. I'm not going to test you on it because it's dumb and it's uncontrolled. So I'm going to just move on. I'm going to change this example. I wanted to be simple, but I'm making it harder by being simple. I'm sorry. I'm changing my example. No. We'll use the simplest promoter first. Sorry, changed my mind because I thought this is going to actually be more complicated than I think it's going to be, and I don't want to do that. So ignore the last 5 minutes or so. We're going to do this. All this other stuff is still true. That hasn't changed at all. Okay, it's just we're going to do an activation step. Okay. So remember what activation is. It's we make 2 radicals out of 0 radicals, and nothing is involved in the propagation. So whenever we're finding an activation, normally we're looking for the weakest bond in the entire system, and normally we add something like this. This is benzoyl peroxide. It is called a radical initiator because it initiates radicals. And why it does that is because it's stable enough that at room temperature it's a thing. And if you heat it, it breaks apart with homolysis. So the homolysis thing is still true. We break that. We get 2 of those. Now, why this works is because benzoyl peroxide doesn't stop here. What it does is it continues to generate carbon dioxide, which is the driving force for why this is so favorable, and a benzene radical. And what's cool about the benzene radicals is they don't like recombining with themselves. You don't like making dibenzene too much. So this is actually kind of stable, and this radical actually exists and can sit around for a moment. So in this activation step, we've made 2 benzene radicals out of 0 radicals at the beginning. In the initiation step, uh, 143, 146. I think hopefully it was that. We're not talking about this, are we, Amanda? Does this make more sense? Sorry, I missed your comment. Was that before I gave up? Okay. I'm going to assume it was just from the timestamp. Great. Can I still go over where the radicals are going, electrons are going? Right. So, thanks, Madison. We have 2 electrons in a bond. We're providing enough heat that the bond just kind of, the oxygen just kind of float apart. Like oxygen-oxygen bonds are weak. Discuss that. And I could go over exactly what the bond association energies are. You don't care, I don't care, let's not do it. Oxygen-oxygen weak. So you got 2 electrons in that bond. The damn thing just shakes itself apart if you heat it enough, and each oxygen walks away with an electron, because no oxygen wants to be O+. Oxygen's fine being O-, right? But no oxygen wants to be O+. So they're kind of pulling, and eventually they separate, each walking away with their electron. And that's what we have here in this middle thing. We have 2 of these with each oxygen walking away with its electron. Now, that's not stable. Radicals are never stable. But what we can do here is we got this carbon, and it's making a bond of the phenyl group, and it's making a bond to oxygen, and there's a radical. So the oxygen electron can start looking to see if it can make a new double bond. And if it can, it needs another electron, because it's only 1 electron, it needs 2 electrons. Where's it going to get the second electron from? Well, it's going to steal it from the carbon-carbon bond. But that's going to leave this phenyl group with an electron all on its own, right? So we can think of this bond shakes itself to pieces so that oxygen can make a double bond with carbon. Why does it want to do that so badly? Because it really wants to make gas. Everything loves making gas. If you can make gas, make gas. So carbon dioxide gets generated. We get our radical here. Okay. So we move on to initiation. So in initiation, we make a radical that is involved in propagation. It's the middle arrow going to the. I just don't see how a ring is formed. No ring is formed. This is a ring. It's a phenyl group. Sorry. Have I not used that abbreviation yet? If I haven't, I'm really, really sorry. Phenyl is a benzene ring. Oh, I haven't used the circle thing. I'm so sorry. I'm so sorry. It's 3 double bonds. We often just draw a circle because there's a resonance all the way around and circles are faster. But this all equal the same thing. Is the middle arrow going to the carbon or the oxygen carbon bond? It's going to the oxygen carbon bond. This arrow is going to that bond. So they're making a new oxygen carbon bond. So the arrow is coming from the bond, and this one is going to the carbon. Okay, so for the initiation step, the most reactive thing, this is always true, always use the most reactive thing in a reaction, your next mechanistic step, is going to be your radical because it's a radical. It's like a carbocation. It's going to be involved because it's a carbocation. And we had this chlorine. Okay. It's looking for the weakest bond to break. There's double bond. We know double bonds are reasonably weak compared to single bonds. And that's what we're going to do. We're going to break a double bond. Okay, so notice how I've drawn this. I've drawn the two radical arrows. Notice they're single hooked as well, because we've been drawing double hooked arrows all the way through this course. The double hooked arrow, like, you know, 2 electron, 1 electron. Double hooked arrow means 2 electrons going. Single hooked arrow is like half as many hooks, so it's 1 electron. I'm sure whoever thought of that thought it was really, really clever. And notice I'm also drawing it so these things are kind of meeting in the middle of nowhere. That's the convention. It's a little weird, but we're showing the electrons are coming from both those places and kind of making a new bond and joining. And if we do that, what do we get? Well, we get that. Now, I drew that radical, not this one, which is why I did not like where my example was going last moment. If I use the green arrow instead, I'd have the radical here. So they're both primary radicals. That needs to be clear. Like they're both on a carbon attached to only other one than carbon. But in one case, the carbon is attached to a chlorine, and the chlorine has sp3 orbitals. And sp3 orbitals can do hyperconjugation, help stabilize that lone radical, the same way they stabilize a carbocation. And I would talk about how to do that on drawing by orbital diagrams, but I'd be lying to you if I did it that way, and so I'm not going to lie to you. I'm just going to say it's beyond the scope of this course, but hyperconjugation works precisely the same as a carbocation, although the reason is different, but all the same logic applies. And so if I was a carbocation, I'd want to be there. If I'm a radical, I want to be there. C with a hat on it means with. You guys don't do shorthand in elementary school anymore, right? We used to have to learn like 1,000 different little abbreviations and stuff. That's the one that stuck with me. Sorry. Okay. Fuck, I'm old. Okay, so we make this one because more stable. Hyperconjugation. Always. So this is a really important rule because it's always true. Like, that's so different from the rules we had with carbocations, actually, to be honest. Everything's always trying to make the most stable thing you can. So we make the most stable one, so we make this one. Okay, so how do you know you've done an initiation step? Because you're involving the thing that is the major thing in a reaction. So if I go back to the reaction, I said, take this and react it. This was the major thing. This vinyl chloride was the major thing. In the activation step, notice there is no vinyl chloride. I have this tiny amount of benzoyl peroxide. It's only a fraction of 1%, like 0.001%. Generally, if I was doing this on the industrial scale, I'd take a ton batch of the vinyl chloride, and I would add basically a crystal of AIBN to it and heat it. Just a tiny amount of radical initiator. It's almost irrelevant how little there is. But, so that's your activation step. It's the one that makes the radicals that then causes everything else to happen for the initiation step. In the initiation, I am involving the species that is the major component in the reaction mixture. So if I then do propagation next, propagation often has 2 steps in it. In this case, it's only going to have 1. There's only 1 species present. And we'll sort of figure out why you can have it up to 2. I'm just going to write the other guy as R. The whole phenyl. Actually, it's only a phenyl. It's not that big. I can be less lazy than that. So this radical looks around for something to react with. It looks around for the weakest bond to react with. The weakest bond to react with is still the weakest bond to react with, which it was in the initiation step. It's still that double bond. So let's do that. I'm going to just do these in 2 different colors because I always find this hopelessly confusing. This is a propagation step. I had 1 radical become 1 radical. And that's involved in that's propagating, that's continuing. Because this is essentially the thing I started with. This is essentially that. And if I propagate again, second propagation step, I've added 2 more carbons and a chlorine, and the radical's still in the same spot. I just extended it by a group. This is why it's polymerization. We're adding 1 group at the same time. Same thing as doing the same mechanism again and again and again and again and again. And the polymer chain is getting longer and longer and longer and longer. Okay. So propagation is where you make your product. The product of this reaction is a polymer of this chloride. The termination step is when we get rid of the radical. So what we might have, and this would be a valid termination step, once you start running out of all the double bonds, because you've just reacted all of it, you're going to at some point have this radical. And the only thing it's going to be able to find to react with is another radical. The most common radical is going to be a polymer like itself, but to save our sanity, I'm not going to draw another polymer. I'm just going to draw the benzene radical that we start with at the beginning, and that's fine. For these polymerizations, we don't really care about termination. You can leave them off on polymerizations altogether. I'm going to get to a point where you can't leave them off where they matter. We want to talk about all the details. But for this one, this termination step, we just have 2 radicals become 0. And it's termination because we're done. Like, this can no longer do anything. It's like we've closed off the radicals. The radicals are dead. So radical reactions follow this pathway: activation, initiation, propagation, termination. Yeah, I probably should. Does the phenyl ever come off? No. It's all my classical education medicine with the C for a cum with the head on top. Okay. I have seen W/, so I think that's in the modern typing generation internet thingy. Yeah, we're exactly you stuff that duplicates you put in brackets. Why didn't a radical react with another styrene benzene radical and terminate the reaction rather than breaking a bond to begin with? I cite it can definitely happen. Nothing interesting happens if that happens, but the main reason is that there's very, very little of those benzene radicals floating around. There's a whole lot of the double bonds. And so it's a whole lot. It's just basically a numbers game. There's like a billion of the double bonds to every one of those benzene radicals. So yeah, it absolutely can react with another benzene radical and kill itself. But there's a billion double bonds to react with first. And that number, that ratio is not actually all that off. Yeah. Okay, let's do another example. I'm going to do what's called a free radical halogenation. So let's say I had methane. I'm going to react this with chlorine and light. No, I'm going to change the example because I won't lie to you if I do that one. So I'm going to actually do a useful example. Okay. Sorry. Isobutane or neopentane, terputane. What the fuck is this? I guess it's isobutane. So we got 4 carbons all attached to each other. Middle one's got a CH, everything else is CH3, chlorine and light. So the first thing we need to do is realize ionically nothing all that interesting can happen here. Right? If you're looking at this from an ionic perspective, and you're thinking, okay, heat, SN2s, E2s, additions to double bonds, I'm going like, fuck all can happen. I've got carbon-hydrogen bonds, and they are boring. And I got chlorine. And yeah, chlorine can shake itself apart, put itself back together, do the hokey pokey, you know, delta plus, delta minus. But nothing particularly interesting can happen with the chlorine ionically. Because so what if it becomes Cl plus, Cl minus? It's just going to form back up together. So that's where we shine light on it, and we do that homolysis. We break apart the chlorine radical because we promote an electron from the sigma bond to the sigma star in chlorine. And so, again, what we're going to do is we're going to do initiation / activation. In this case, they are the same thing. Why? Because there is no outside initiator. We're actually initiating something that's going to be involved in propagation. Do we know that yet? No, we don't know that a priori. You don't need to know that. You're just going to go like, oh, I guess that was propagating now, wasn't it? Okay. So you shake the chlorine apart with light. Okay, so we have a chlorine radical. Now, the chlorine radical is going to react with the weakest bond in the system. What is the weakest bond in the system? You got chlorine, you got this isobutane thing. Amanda asked, are brackets used for reaction other than polymerizations? No, it means polymer. Like it literally means polymer. Except when we put big brackets around something saying everything's transition state. Close faith, I think you've identified the second weakest bond in the system. What's the weakest bond? Dudes, you're all coming up with the second weakest bond. Right. Olivia with the win. Chlorine is but it's unproductive. Exactly. Let's just think about that though. 99.999% of the time that this chlorine is going to do something, it's going to react with the weakest bond in the system. And Olivia is absolutely right. It is unproductive. But this answers the question of why it does it. That is unproductive. That is the major reaction. But we didn't know any reaction occurred. Like nothing useful happened. Okay. Very, very occasionally, it reacts with the second weakest bond in the system. So what's the second weakest bond in the system? Well, Faith and Madison got us. It's the CH bond. Why is it so? Which CH bond? There's two different types. There's methyls, and then there's the tertiary. Shit, oh no, I did drop my Pepsi. Oh god, I got Pepsi everywhere. Peptacular. Any opinion on which CH bond? I'll give them colors. Red or purple? So why are you saying that, Madison? There's 9 of the others, only one of those. You're right, by the way. Like, it is that one. Do you know why it's the weakest bond? Anyone else know why it's the weakest bond? Nope, no induction. what we literally do if we break that bond is we literally split the radicals apart, right? Those cancel out. They're both H dot, same energy, they're the same thing. This one is a tertiary radical. It is stabilized by hyperconjugation with all the adjacent sp3s. This is a primary radical. It is not stabilized by hyperconjugation with all the adjacent CH3s because there's only one adjacent sp3 hybridized atom, which is the carbon. Primary, tertiary. Tertiaries are more stable because of hyperconjugation. The bond, that CH bond is literally the weakest bond in that molecule because the resulting radical is more stable. It's kind of circular logic. You break the weakest bond to make the most stable radical, and it's the weakest bond because it makes the most stable radical. But it only seems circular. It really is the most stable radical is what makes it the weakest bond. Okay. So 99.99999% of the time, that chlorine radical attacks chlorine gas, generating another chlorine radical. Who gives a fuck? Very occasionally, it attacks the purple hydrogen. And then we get something productive happening. We often wouldn't write this top one, but I think it's, hopefully I wrote CH3. Oh, I wrote Cl3, didn't I? Okay, Faith, there we go. I think you've added like 2% to your final grade. So, good catch. The radical is, this is the most stable radical that you can make out of that. Notice it's the second most stable radical in a system. So as soon as we make it, what's that going to do? Like, it's not a good radical, it's just the second best one. Perfect, Olivia. It looks for the weakest bond in the entire system. That's still chlorine-chlorine. So you make the second, you broke the second weakest bond. Doesn't change what it wants to do. It still wants to go after the weakest bond. Radicals are fucking lazy. They go after the weakest bond. It is always the weakest bond. And unlike ionic reactions where we had to take all these other factors into account, all the sterics and the, well, mostly sterics, radicals don't worry about that. They're just like weakest bond, go after weakest bond, chase down weakest bond. They're all about the weakest bond. And when the weakest bond is non-productive, they're still all about the weakest bond, but we just don't care because it's non-productive. Then they go after the second weakest bond occasionally. Could it also react with another chlorine radical? Yes, that'll be a termination step, Christian, and that's going to be much rarer because the number of radicals at any one time is very, very low. You're going to have a metric fuck ton of starting materials that haven't turned into radicals yet. So at any one, like literally in a Pepsi bottle like this that I've got, if this bottle was full of isobutane and chlorine in a 1-to-1 molar ratio, and I was shining a light at it, I would probably have like 2 to 5 radicals in there at any one time. Like I just wouldn't have very many radicals. Like think about how many molecules there are. It's on the order of 10 to the 21 or 10 to the, that's a liter. Water is 55 moles per liter. So isobutane is probably about the same. So no, probably on the order of 10 to the 24, 10 to the 25 molecules present in my Pepsi bottle. And there will be maybe 5 radicals. The chance of 2 radicals finding each other is not good. The chance of radical finding anything else except a radical is very, very good. So that's why propagation steps dominate, because you just have such a good chance of finding something that isn't a radical. When you use light, will initiation activation always be a combined step? No. It is. It's not because it's the light that combines them. It's because the thing that's getting activated is involved in propagation. Chlorine is getting involved in here. We're going to actually see examples where you can use light to activate benzoyl peroxide. And benzoyl peroxide will not be involved in propagation, but we're going to be initiating it or activating it. Okay. Note, this is where we make our product. And we know we're done propagation when we regenerate the initial radical that came into the sequence from initiation. So initiation gave us a chlorine radical. We have regenerated our chlorine radical. So you know to react to the second weakened bond when the weakest bond is unproductive? Exactly, Amanda. That literally is it. That's how radicals work. So termination here is going to be combine all the radicals in all different ways. So you can have a chlorine radical plus a chlorine radical combining to give us a chlorine 2. This, strangely enough, gives us more product. And so people do get confused saying, hey, look, I made my product. Yes, but it's kind of an accident of termination. It's an accident mechanism. The amount of this that's being generated from termination is trivial compared to the amount that's being generated by propagation. Like, you could not even include it, wouldn't make a difference. Be like the 10th decimal place. It just doesn't fucking matter. It's about how much is coming in from the propagation. Sorry, why is it unproductive? This is what we call reaction, which gives you the same things on the left and right hand side of the arrows. So on the left hand side of the arrow, we have a chlorine radical and chlorine. On the right hand side of the arrow, we've got a chlorine radical and chlorine. So this is an unproductive reaction because the thing on the left is the same thing as the thing on the right. That's the textbook definition of an unproductive reaction. It means it doesn't do anything useful. Yeah. And then theoretically, and everyone gets really excited about this one. Like literally. Because I see this all the time as being, this is what the product of the reaction is, because it looks like the most complicated thing you can make. It's not the product of the reaction. You will never be able to find it if you're looking like analytically at the system trying to find this thing. It's not going to be, you're never going to be able to find it. It's minor component, totally minor. Products come from propagation. Okay. We're at time, so I'm going to leave an example for class. And we're going to do we'll take this up next class to start next class. It's a very, very, very classic. By heat, I mean about 80 degrees. AIBN. I definitely have done this in the lectures, so if you follow up on the lectures, get it. So what's the product of this reaction? And What's the mechanism? What I am going to say is it's not the same product you get where we were doing this chemistry back a few weeks, a month ago. But it might be a good idea to work through that and figure out exactly why you get a different product. No, it's not a radical, it's just a dot. That's because I don't write these neatly. Well, I'll tell you this, if you take AIBN and you heat it, again, that whole thing of stuff wanting to become gas, nitrogen gas is what everything wants to become. So we get two of these isopropyl radicals. Look at the stability of that radical. We're going to start next class by talking about the resonance in that radical and why it's so stable, which is why you don't need very high heat to make it happen. And then we will walk through that mechanism, but I encourage you to try it yourselves. It's also some of the assignment questions. So this is a good idea. So can I explain, sorry, Amanda's saying, can I explain what's going on in termination? So assignment number 4 is going to cover up to, E2, SN2, no radicals on assignment 4. But Markovnikov, anti-Markovnikov additions to double bonds, epoxidations, ozone, SN2, E2, E1, SN1. Yeah, that those modules. So can I explain what's going on in termination? So in termination, 2 radicals are becoming 1 radical, or becoming 0 radicals. So we're just remaking bonds with radicals recombining. It's the exact opposite of activation initiation, where we split molecules apart, shook them apart. Now they're coming back together, and we're making stable molecules. So I'm combining all the, like, radicals don't care. Radicals are so promiscuous. They will react with any other radical. They will react with the weakest bond. But they don't want to be radicals. So any 2 radicals can come together. So in this termination step, we have 3 ways to get rid of the radical. We had chlorine radicals, we have the isobutyl radical, and 2 chlorine radicals can combine, 2 isobutyl radicals can combine, or a chlorine radical can combine with an isobutyl radical. There's actually other ways that this can happen, but we won't think about that for now. When's the best way to tell if you have a radical mechanism? Light is normally a good clue, or if you have one of the radical initiators. So we've seen AIBN, and we're going to see benzoyl peroxide. There are lots of others. I am not going to use any others in this class. It will be either AIBN or benzoyl peroxide. Are we required to provide all these ways to get rid of the radical? Yeah, there's always going to be 3. Because you're always going to have 2 radicals in your propagation, and so you're always going to have 3 ways to kill them. Yes, you are required. Can you add like a single radical as a bonus, or does the practice assignments have a lot of good examples? Mohammed, I think I have an entire assignment that's basically radical stuff. So I think there's quite a bit of radical practice. You don't want to be evaluated on something this quick. Or maybe like as a bonus. No, we'll do it later. There's the practice assignments have examples, and the textbook also has lots of examples. Okay. I think I've answered everyone's question. Have a great day. Good luck. Enjoy the rest of your Monday. It's kind of sunny outside. It's nice. I was driving across southern Ontario yesterday, and it was one of those things where you go like, thank God I live in Windsor and not in some of those snowish hellscapes. I come from Ottawa, which is a frozen hellscape. It's the best definition of Ottawa. And so it is really nice being down here. Okay. Bye. I'm going to enjoy the weather.